Okay. All right, so today we'll wrap up chapter 3 and talk about box plots. Okay. So box plots are another display for numeric data. What are the other displays that we have for numeric data? Okay, so other displays, we have histogram, and I heard stem plot, and what else? And the dot plot, okay? So these are all for numeric data. Okay, and so a box plot is basically just a kind of a quick summary, a way to just quickly summarize or just show the bare bones essentials of the data, okay? So shows the quote, just the essentials of a set of numeric data. Okay, so the components of a box, or a box plot, also called a box and whisker plot, may look something like this. So you've got a box, you've got whiskers, and then you've got some, maybe you have some dots, okay? So the boundaries of the box, this is Q1, this boundary is Q3, and this line right here is the median, okay? So those are the three spots that define the box. So the width of the box, what is the width of the box equal to? The width of the box is equal to our IQR, because it's the distance from Q1 to Q3. So the width of the box is our IQR. Okay. Based on the box, okay, so if this is our IQR right here, what we do is we take 1.5 times the length of our IQR. So, I don't know, so I take this length and I multiply it by 1.5, so who knows, maybe that's something like right here. Okay, so this is going to be 1.5 times the IQR. And I go out this direction and that far in that direction, and I do the same in the other direction. So I go 1.5 times the IQR above that way, 1.5 times the IQR down this way. This creates these invisible boundaries called fences. Okay, so this is the upper fence, and this is the lower fence. Okay, and so again, you have the width of the box, and then you go 1.5 times the width of the box above, and 1.5 times the width of the box below. So the upper fence is going to be Q3 plus 1.5 times the IQR. And then the lower fence is Q1 minus 1.5 times the IQR. Okay? And so the fences differentiate between what is considered an outlier and what is not an outlier. Okay? So data points outside of the fences are considered to be outliers. okay? Or I guess I should say potential outliers. And there are different rules, different methods for deciding what is an outlier or what is not an outlier. This is a pretty good method. Go 1.5 times above Q3, 1.5 IQRs above Q3, 1.5 IQRs below Q1. These set up these kind of these invisible boundaries. If it's bigger than that, if it's above over here, outlier. If it's below down here, we'll also say it's an outlier. Okay. The whiskers, and I guess depending on which textbook you read, maybe some of these rules are a little bit different. Okay. Our whiskers extend to the largest data point and smallest data point that is not an outlier. Okay, so don't just go straight to the fence, okay? Find the largest data point that you have that is not an outlier, and the whisker ends there, okay? So extend to the largest data point and smallest data point that is not considered an outlier. So if your smallest data point is not an outlier, then it goes just to that point, all right? Otherwise, the whiskers go there, okay? Is that all right? Okay, and so with a box plot, let me just save this, stats 10. So with a box plot, you just really get a sense of kind of the range of the entire data. The IQR, you get a sense of its spread. You also get a sense of where the median is. You can't see if it's unimodal or bimodal, so it's not going to show as much data or as much detail as a histogram per se, but you can see if something is left skewed or right skewed or things like that. You can see how far the whiskers extend, and that'll give you a sense of whether it's left skewed or right skewed. Okay, so for example, if you have a box plot that looks like this, okay, this would be an example, assuming my whisker is not going more than 1.5 times our thing, this would be left skewed. Okay, because we can look at basically where the median is. This is the median, and we can see, how far do our data points go, and we can see we have extreme values to the left, but in the opposite direction, it doesn't go that far, right? So left skewed, we have extreme values to the left, but not the right. So that would give us an indication of left skew, okay? You can kind of also, if you have something symmetric, the box in of itself may not be symmetric, but if you just look at kind of the distance to the ends of the whiskers, and you say, okay, well, how far is it from, or not even just the whiskers, but if you have, assuming we have no outliers, so how far is it from the min to the max? We can kind of see, here's the median, here would be the maximum, and here's the minimum, and this is gives us the sense that our data is, pretty symmetric. Okay, so just looking at a box plot, we get a sense of the data. Okay, but what we cannot see, all right, if the data, you know, is unimodal or bimodal or whatnot. Okay, but you can start making comparisons pretty quickly, I think, between box plots. So if I can flip to the next slide. So you know, if you have one box plot that looks like this, and then another box plot that looks like this, okay, we can see that you know, the minimum and Q1 are in about the same location. So if this is group 1 and group 2, so you know, at the lower end, the minimum and Q1 are about in the same location, but we see what? The median for group 2 is much higher. Group 2 is higher than group median for group 1, okay? And in fact, the median for group 2 is higher than Q3 of group 1, okay? Okay, and so, you know, just kind of comparing these, and we see, you know, Q3 of group 2 is right around where the maximum of group 1 is. Okay, and stuff like that can happen. Let's see. So, you know, just from looking at box plots, you can get a good sense of where the data lie. Another thing that we can draw from box plots is, oh wait, what was I going to say? So yeah, so we can make these types of comparisons. Also, am I trying to say something about these? Yeah, so we can make, I'm sorry, I totally just lost my complete train of thought, and I'm trying to think what else I'm trying to say about these. So also higher than Q3 of group 1. Oh, yes, okay. And if we ask, you know, what percentage of the data, so in each of these we can split the data like this, and we can say, you know, 25% of the data lies from here to here, 25% is in here, 25% and 25%, okay? If there are outliers, okay, let's say with group 1, we had an outlier out here or something, okay? The outlier is still considered part of that 25%. Okay, so from there, you know, you could just say in the span between, you know, the median of group 2 and group Q1, you know, 25% are between here and here, whereas for group 1, you know, half of the data is in that same range. Okay. All right. Are there any questions about box plots here? Yes? Is there a formal way to distinguish outliers? So, well, I just gave you one, which is you go to, you draw your upper fence and your lower fence at, you know, Q3 plus 1.5 times the IQR, and Q1 times 1.5 times the IQR. So that's one method, okay? And that would be considered a formal method for determining what's outliers and what's not. There are methods, other methods that I would say are beyond the scope of the course. But the good old, I'm going to look at the histogram and just eyeball it is pretty good also, okay? Our brains have developed kind of this ability to make patterns, okay, or identify patterns and identify things that are, quote, unusual, and that's pretty good, okay? So yeah, it's good enough for most purposes like that, okay? But yeah, are there formal methods? Yes, there are formal methods. The upper fence and lower fence is a good method, all right? Okay, is that okay with box plots? Any questions or issues there? Okay, so we will wrap up chapter 3 there. You guys have a quiz on Tuesday in your discussion section covering, I would say, up through this stuff in chapter 3, okay? I'd say, 95% of the quiz will be about as tough as stuff covered in lecture and homework. There might be like one question that might be a little bit tougher that you have to do some thinking about, but it should be okay. Next week we'll also start using the clickers, so make sure you have one and have it registered by then. I generally make the clicker questions hard, okay, or like tricky per se in class. So don't be upset that you're getting these hard questions on the clickers, and I do that as such because I feel like these hard questions then allow me to enter cover more topics in lecture, but also forces you to do some thinking about it before we get into those topics. So anyway, we do that. Okay, well, so that wraps up chapter 3. I'm going to go ahead and just start chapter 4, and then and we'll go from there. Okay. I'm sorry. Was there? Okay. Sorry. All right. Okay. So now we will begin chapter 4. Okay. So chapter 4. We are still kind of in the land of descriptive statistics, but now we are looking at describing a relationship between two numeric variables, okay? So chapter 3 was all focused on looking at one numeric variable and describing its shape and distribution and all of that stuff, okay? Chapter 4, we're going to look at two numeric variables, and we're going to see if we can describe a relationship between these two numeric variables, okay? So for example, we can say, I hope nobody hates snakes too much, but let's say we decided to look at a species of snake, okay? And I don't know, we have, let's say we have 10 specimens here, okay? And we're gonna take two numeric measurements, okay? The first one is we're going to measure the length of the snake, and we'll call this. And then we've got the weight of the snake. Okay. And with these two, we generally assign the letters X and Y. Okay. And we want to know, is there a relationship between the length of a snake and the weight of the snake? Okay. Okay, and so, what do you guys think? Yes, right? I mean, so, just imagine, okay, so this is my beautiful artwork here. So here's a snake, okay? Yes, all right? And then, and here's another snake that is longer. All right, okay, which one weighs more? Like, if we had to guess, all right, we would guess that the longer one weighs more, right? So we would guess. Well, I mean, this is like, okay, all right, this, I have to make him a little more uniform in thickness here. Okay. Anybody identify with House of Slytherin? Okay, never mind. Forget that I even said that. All right, so we would guess that this one weighs more. All right. All right, we would just expect, longer snakes, probably more weight. Okay, that's what we would anticipate. We could actually, oops. So let's say, so x is, what is this length? Okay, so I don't know. Let's say these are like little snakes. So they're like 14 inches and 12 inches and I don't know, 10 and maybe 16. Okay. And then the weight, I don't even know. How much would this thing weigh? All right, so I'm going to just make up some numbers here. 10 ounces and 9 ounces and 8 and maybe 12. Okay, and so we would graph these in a scatter plot. So what is this? 10, 11, 12, 13, 14, 15, 16. And then 7, 8, 9, 10, 11, 12. Okay. Okay, so 10, I draw, so this will be length down here and weight up here. Okay, so I'm just graphing these coordinate pairs here. So it's actually, it would be, the length is 14, so that's right here, and we get a dot at 10, okay? And then the length is 12, and we get a dot at 9. And then a length of 10, and then we get a dot at 8. And then at 16, we have a dot at 12, okay? All right, and so, just looking at these dots, does there seem to be a relationship between the length of the snake and its weight? We would say yes. It appears that longer snakes tend to weigh more than shorter snakes, right? Okay, well, when describing a relationship between numeric variables, there are a few things that we want to make sure that we discuss or mention, okay? So we, And these things will be direction, also called trend. We want to describe the strength, and then the shape. Okay. So the direction can either be, positive or negative, or maybe neither positive nor negative. Okay. As far as strength goes, we can have strong or weak, and really anything in between too. Okay, moderate, kind of strong. Okay, and as far as shape goes, in this class we will just talk about linear or nonlinear. Okay, so if it's not linear, it will be nonlinear. Now, in another statistics class, you can further just split up linear, the nonlinear ones into, geometric or exponential or quadratic, things like that. But in this class, we'll just have linear versus nonlinear. Okay, so let's talk about each of these things. So as far as trend or direction goes, if we have a positive trend, positive trend at its very basic just means large values of x are associated with large values of y. Okay, and likewise, small x associated with small y. So this, the snakes would be an example of positive trend. Okay, snake weight, length, and weight. Snake length and snake weight has positive trend. Okay, so the general graph there looks something like this. If you had to make a scatter plot, you have dots going up and something that goes like that. Okay, so as x gets bigger in this direction, the y values get bigger. Okay, so large values of x over here, if we look at the dots, they're associated at the top for large values of y. Over here, if we look at small values of x, the data points down here also go with small values of y. Okay, negative trend, we just have the reverse. So large x goes with small y, and small x goes with large y. Okay, and so the general trend would be something like this. Okay, so, small x, if we look at small x right here, they go with large y. Meanwhile, large x goes with small y. Okay, so something that might have a negative trend would be something like mileage on the vehicle. And resale value. Okay, so Vehicles with low mileage will tend to have higher resale value. Vehicles with high mileage will tend to have lower resale value. It's overall general trend. Of course, lots of other factors go into determining resale value, but if we had to say, is there an overall trend between the mileage on a vehicle and its resale value, this is what we would have. Okay, so that is positive or negative, and then, you know, if it's neither positive nor negative, okay, you know, something that looks like this. Okay, where you have a kind of that. This is, you know, a flat trend. Or maybe you just kind of have something like this. Okay, so this could be something like we could look at someone's IQ score versus their shoe size. Okay, and we would not see neither a positive nor a negative trend, because you would have people with high IQs with large shoes and people with high IQs with small shoes, people with low IQs with large shoes, people with low IQs with small shoes. Okay, something like this would be I don't know. What would this be? Okay, number of slices of pizza you eat versus, I don't know, something that's going to remain relatively constant, hours of sleep. Okay, so on days where you eat lots of pizza, you might get 7 to 8 hours of sleep or more or less. Okay, on days where you didn't eat any pizza, you might still have a small range in terms of the amount of sleep. So you know, unlike shoe size where there's going to be a large range, you know, in terms of hours of sleep, it's probably going to range, well, in college it's very different, I guess, but you know, outside of college, most people get a fairly regular amount of sleep, okay? Yeah. And, okay, or, you know, you have other things, you know, something like this, right? This could be time after liftoff, and this could be altitude. Okay. Positive for the first half until gravity takes over, and then it's negative, right? So this is neither, these would all be neither positive nor negative. Okay. However, you know, if we had truncated this, okay, if we did time after liftoff and it ended there, we would say the data here shows a positive trend, okay? Because we don't know what's going to happen over here, all right? I mean, if I told you this is time after liftoff and altitude, then you could guess what's going to happen over here. But if it ends right here, then based on the data we have, there's a positive trend, right? So for this data, based on the data we see, the overall trend is positive. Okay, is that all right for this one? Okay, so just based on the data that we've seen here, the overall trend would be positive, okay? But over here, neither positive nor negative. Okay. And then we have the strength of a relationship. Okay. And there's a few ways we can think of this. One can be, can we make good predictions for one variable based on the other? Okay. Or another could be, how much scatter is present in the dot plot, or in the scatter plot. Okay. So if you have something that looks like this, this would be a strong relationship. Okay, and we can see, okay, there's not a whole lot of scatter, so little scatter. Okay, and then if I gave you this particular value of x, and I said make a prediction for what y would be, you would be able to kind of create this small range and say, okay, well, I would expect y to be kind of in this vicinity here. Okay, so you can have a fairly small range for your prediction. On the other hand, we can have lots of scatter. Maybe even more. Okay, so overall we still have a positive relationship. So still a positive relationship. Okay, but this would be a weaker. And as far as strength goes, it would be a weaker relationship. Okay, we see a lot more scatter. And given a particular value of x, what is kind of the range of values for prediction, you'd probably guess right in the middle, but there's really a wide range that y could take on for this particular value of x. Okay, so y can take on a wider range of values for particular x. Okay, so that's kind of the idea behind strength. So, if we think of certain pairs of variables, we can say, what's going to have a strong relationship versus a weak relationship, okay? So, for example, we could take someone's height. So x could be a person's height in inches. And y would be a person's height in centimeters. So the same person's height, okay? Okay? And this would have a strong or even a perfect relationship, right? Strong, perfect relationship. Because based on one variable, we can make perfect predictions for the other variable. Okay. you know, for, let's see, other things that would have a strong relationship, we could take a person's height, and then y could be a person's, what is this, arm span? Okay. All right. Now, some people have relatively short arms. Some people have relatively long arms, okay? And, you know, we see kind of these extremes show up in, like, sports and athletics where, you know, you expect certain things and whatnot. But in general, taller people are going to have longer arm spans, and this will be, you can make pretty good predictions about someone's height based on their arm span and vice versa, okay? So this will be, you know, a strong relationship. Okay, some scatter, but not a whole lot. Okay. And then lastly, we could have, you know, a person's height and the person's weight, right? And this would have, you know, either a moderate or a weaker relationship. Moderate to a weak relationship. Okay. In general, taller people weigh more, shorter people weigh less, but there's also, based on someone's height, I think you would have a hard time making a very good prediction about the person's weight, okay? Because there's probably a lot more variation there, okay? So, in general, a positive relationship. Okay, but predictions of weight based on height will not be, cannot be expected to be highly accurate. So these are just kind of examples covering certain, some of this stuff. Okay, and then lastly, let's talk about linear versus nonlinear. Okay, so linear would just mean a straight line can summarize the overall relationship. And nonlinear would mean anything where a straight line does not work. Okay, and for, you know, deciding whether something is linear or not linear, we're just going to depend on our eyes here, okay? As far as, you know, the scope of this course, we're just going to look at it and say, that looks kind of like a straight line, and that one does not, okay? Because more advanced tests would be, yeah, beyond the scope of this course. So, you know, you look at something and you go, does a straight line work here? Sure, okay? So we would say linear, you know, even with a few points that are kind of out there, all right? And then whatever, if it looks like it's curving something like this, okay, we would say, oh, nonlinear. I know this sounds so silly, but But really, that's all we're gonna do, okay? Just use your eyes, and that's fine, okay? Okay, that's it for today. We'll have a good weekend. We'll see you guys on Monday.